It's
Yeah.
just the nature of the game. I was speaking to a researcher today about writing a paper about Bittensor subnets, and he seemed very confused. Like, how could we ever possibly write a research paper about a subnet on Bittensor when you don't know what the miners are doing? And it took a little while, but he eventually understood that the purpose is to
Subnet.
investigate the algorithm, the incentive mechanism. That's actually the technology.
Yeah.
Is the mechanism that you guys have invented. In the same way that you would study, an algorithm for training a neural network, you wouldn't study the individual activation or like, the behavior of a single neuron in a neural network. That's not the point. The point is the epiphenomenal value of what's being created.
Yeah.
So here we are.
We have the same when you talk to a potential Web 2 partner that wants to sort of understand how you're not the one that controls the generation per se, but you're the one that sets the rules of the game, and the incentive design for it. So
And I think without further ado, we can maybe start that conversation, Ben. Up to 100 people in the chat. We got the YouTube links going. We got Craig recording. Ben, thanks for coming up on stage. Let's chat 404 17.
yeah, thanks, Const. I'll hop into it then. You've got a couple of our team members on stage. You've got Max and Monica. Max is our tech lead. Monica is our marketing and BD lead. So I'm the founder of the company that eventually became Subnet 17. And I think today we're just going to run through a bit of an overview of what we're doing, what we're building, why we think it's important to build this and relevant to build this on Bittensor. We'll also try to cover a bit of our incentive design and validation. Even, as you noted, Const, we're about a year now on mainnet, and so we've seen a lot of changes and iterations to that. So we've got some of that learning here of how we changed. And then I think I'd like to just end with some of the cool stuff that's being built, not even just only by us, but actually by third parties that are using our APIs. So that's the goal. I won't give kind of like a detailed background on all the team members, but we're about 10 people now. We come pretty heavily from the research side, and also with experience in 3D, in gaming, and in film, VFX, and metaverses. So yeah, just the company actually is a bit older than Bittensor. So we come at this from a Web 2 perspective. We started pretty heavily with EU research funding. So we're based out here in Europe. And what the interesting thing for us, or for me, when I saw the Bittensor white paper, is it just made a lot of sense to me. So as a Web 2 company, what we did is a lot of working with existing, mostly game developers, but really kind of AAA, which is just a industry standard for very high quality game developers, to build out their virtual worlds. And we're using things like image processing and computer vision, segmentation networks to basically allow them to do more with what they already had. But when I saw the white paper for Bittensor, what I realized then was that it was an opportunity to do more like democratization of content creation. So not just target only the really big studios, but open up a lot of those possibilities for smaller indie game developers, work more on the kind of foundational layer of this tech stack, which I'll go into. But I figured it's helpful because I don't know how deep into the gaming and entertainment industries everybody is here. I'll just give a brief overview of what these industries look like and the problems that they're facing. So in a way, this is kind of summing up the problem. Basically, that as compute and graphics have grown exponentially, the demands of people for what virtual worlds should look like and how they should behave is growing in importance, and it's also growing in time and cost for game developers, for studios, for film that are working on it. So what I would say is that it's not just the main character that everybody cares about. That's sometimes what people think about, but in most games and immersive experiences, it's everything in the world that takes so long. So all of these objects that you see here, these are all 3D objects. These are all textured and modeled by hand so that somebody can create an immersive feeling for a virtual world. And this is a pretty big problem in the gaming industry. So Grand Theft Auto 5, for example, which is this smaller map on the right-hand side here, this took them about 5 years and cost around $265 million to build. But the budget was leaked for GTA 6 at $2 billion, which is kind of insane because it's larger than the GDP of some countries, actually. And so the industry as a whole is seen as being quite big. So 300 billion is the gaming industry there. But I think that's not really a limitation on what outputs of our subnet should be focused on. So we're seeing people work with things like film and VFX, digital twins, metaverses, XR, all of these other really interesting applications. So that's generally the markets that we cover. But in terms of why we wanted to do this on Bittensor, I think one of the things is we're ideally building here a subnet like an intelligence subnet, because 3D AI right now, there is no clear winner in the 3D AI space. There is no dominant even form of representation, let alone model that's winning. So there's a fragmented landscape here for how 3D AI is developing. Some of the three main protagonists in this story would be meshes. This is the industry standard for the industries of like the entertainment industries. Then you have NeRFs, which are neural radiance fields. This comes out of like a reconstruction background. So these were used predominantly for doing things like reconstruction of existing structures or existing buildings, for example. And then Gaussian splats, which is somewhat newer and kind of combines a little bit of the elements of both meshes and NeRF. So yeah, my opinion here is that this is about to explode. So when I look at how we saw the 2D AI networks develop and then reach a critical mass and then start growing very, very quickly, we see that happening now with video, and I think 3D is what's to come. So I think it's a really good time to be mining on our subnet, because essentially what we have is this combination of there's no dominant solution, there are rapidly growing use cases, there's a large ecosystem of open source, not just foundational models, but really like dependencies and combinations that miners can put together to achieve higher quality results. And I think that's really good for Bittensor. That's really good for miners within Bittensor when there's no dominant solution, because it just means that you're really incentivized to find the best solution. I think one example that we've seen of this is like if while we're on this call, for example, there's some new paper released by Microsoft or NVIDIA with an innovation in open source that will help generate higher quality models, we would see miners already test and deploy that on mainnet within a series of days, if not hours. And that's really nice, because that's a sort of speed of growth within this kind of rapidly changing ecosystem that like a centralized competitor wouldn't really be able to match. So I think here, if we want to have a longer form discussion and Q&A about the different types of 3D representation, we certainly can. But I think we do write a lot about this on social media, so I won't go super deep into it. But I think, you know, what we see is that NeRFs are really the standard for high fidelity reconstruction. So they're very good for a certain level of realism that comes in. Gaussian splats are the ones that are gaining momentum within the AI research communities, and meshes are the ones that are most compatible for existing pipelines. So our team is really focused on Gaussian splats, because that seems to be the one that takes the benefits of both. That's the one that can do the high quality reconstruction fidelity that NeRFs can do, but at a fraction of the memory usage, at a much faster speed, which is needed for many gaming and entertainment use cases. At the same time, against meshes, meshes have limitations into the complexity of geometry that they can handle, and the way that their rendering pipelines deal with different levels of detail. But I think maybe just to show it would be a little bit easier. So this is a stereotypical use case for a Gaussian splat that I think is kind of interesting here, because if you would model this cat laying in the bed using traditional techniques, one, it would take an insane amount of time to achieve this level of detail. And two, it would be computationally very, very heavy to do it. So what a Gaussian splat does here is achieves that through a much lighter weight process, something that's then able to be deployed into web viewers or 3GIS systems. And then, yeah, we're not ignorant though of the fact that not, despite that this is an standard processes to convert Gaussian splats into meshes. We're not the only ones that have built these types of processes, but we've built ones that people use them for whatever their purposes are, including converting splats that are generated off of Subnet onto be used in their application.
Before you, Ben, can you actually just explain like what the difference is between and a mesh? Like what we can see the difference there in that image, but what actually does that mean technically for the representation of this object?
Yeah, so a mesh is going to be probably what most people are familiar with. It's going to be like a polygon-based, excuse me, a polygon-based form of representation. So you're going to have like a shell structure made up of various faces, connected by vertices, and then there will be color. Yeah, it can be triangle, can be quad, depends a little bit on the use case. The way you would texture those meshes are you might have color data baked into the vertex of each of these mesh points, or you might have it on the face, projected onto the face of the mesh, and that's how you would define an object. So if you think about this cat, for example, you will need an individual polygon or small clustering of polygons to represent each hair or fur in order to achieve that level of fidelity. And there are certain rendering techniques that can alleviate this. So you can use render instances so that maybe it's just a handful of hairs that get distributed over it. But even still, it's very computationally heavy as a process. Difficult to manually model and computationally heavy as a process. Gaussian splats are a bit different. So Gaussian splats are like a point cloud on steroids in a way. So instead of having just a traditional point cloud that would come from something like a scanning, each of the points has its own unique scale and rotation in all three coordinate systems, X, Y, and Z coordinate systems, and a color and opacity to it. So here, what you're able to do is you're able to have a piece of geometry. It's a little bit misleading to call it a piece of geometry, but I think it's easier to understand that way. But a unique piece of geometry that's sort of stretched and pulled in different directions that when viewed give you a very, very realistic outlook for a particular object. So actually, in this way, because you're still at a base of a point cloud, you're very lightweight, you can generate them very quickly, and you can tap into a lot of the AI techniques that were used in training neural radiance fields or NERF models for AI processes.
And so it matches better to neural networks, for one.
Yes, absolutely. I mean, I think it does that on the AI side of stuff. It matches better with neural networks, but on the deployment side, I think our team is really bullish that this is going to fundamentally change a lot of games and virtual worlds, and we're already seeing that to some extent, which is that you're able to do more pieces of unique geometry. You're able to have larger scenes because you're not bound by some of the limitations for how heavy and how computationally intense meshes are. I mean, meshes have been the standard for many, many years now. So I think what we're seeing is there is this new form of 3D representation in Gaussian splats that has all of these benefits. It just doesn't yet integrate into some of the existing workflows of the industry, but because it has the benefits, we're seeing people start to build new tools around them. And already there's plugins to work with splats in all of your major pipelines, and to some extent where we didn't find sufficient quality metrics to build with splats in something like a Unity or an Unreal, which is the largest game engine. We built them ourselves and then made the plugins open source.
And that might be because there's actually like hardware accelerators to work with meshes, whereas they don't have the same hardware accelerators for splats. Correct.
Exactly. I mean, it's not just hardware accelerators. It's a whole ecosystem built around, a digital sculpting tool would be traditionally oriented around sculpting a mesh object instead of sculpting the point clouds that come from a Gaussian splat.
And just so I understand the point cloud, I hope I'm not taking too much of the time in the presentation, but I think the audience would be curious. So in a mesh, I can imagine it like a bunch of triangles or polygons, right? It's a set of polygons that they have a face, right? And there's color to that face, and a whole trillion of them make a highly complex environment. This point cloud, you said it's just a set of points, and this describes the surface. How exactly does that work? And what are these points actually representing if they're not surfaces, or are they surfaces?
No, so they're not surfaces. So point clouds. So the starting point here would be a traditional point cloud will come from something like if you scan an object with a handheld scanner, or even with a technique like photogrammetry, which is a non-AI technique where you take multiple photos of an object. You use procedural algorithms to triangulate those points in space. And then you have basically an XYZ coordinate for various points of overlap and reference that you can find. And with that, the density of that point cloud gives you an approximation of the shape of the object that you're looking at. Now, historically, what you do is you take that approximation of the shape and you connect all of those points with faces, with triangles, and you convert it into a mesh. And that becomes now your surface-based or your mesh-based object. In the case of a Gaussian splat, rather than connecting those points by faces, which is a pretty heavy and computationally intense process, what you do is you basically start to stretch that point in an X, Y, and Z coordinate system that is not uniform. So your Z scale can be larger than your X and Y scale, and you start to rotate it, and then you give it a color. And so it's the overlay of these different points and the color of these points. So you could think of them as little like ellipsoids in a sense. It's the combination of this that give you the feeling of having a concrete geometry that does not exist.
Wow,
and that's actually kind of similar to how a radiance field works as well. So it's kind of these layers of transparency in a radiance field that give you, again, this kind of indication or feeling of a solid object when no solid object exists. But it's able to be converted to a mesh if you need a solid object in order to work within the constraints of different systems. But if you don't convert it to a solid object, it's able to be far more lightweight, far more kind of aesthetic in many ways than a traditional system would be. Yeah, cool. Yeah, and this is just to show that. So it's not necessary for every object that you'll work within, and so sometimes meshes and other times you want to keep them as Gaussian splats. Yeah, so jumping a little bit to our incentive design and how do we decide what is a good model and what is not. I think this is pretty interesting in our subnet that is maybe not a problem that all subnets have, but in our subnet, there is no ground truth, because there are elements of subjectivity here. So if in this case, these are two real results that I pulled off mainnet. So the prompt was a sturdy yellow drill cordless, and even as a human, it's difficult, I would say, to decide if one result is better than another, and that's kind of the difficulty that we as a subnet are faced with. And I'll get to how we solve it with this specific example as well. But I think the first thing we start to do is look at like a framework that we can work with here. So we don't need to go through kind of this overly dominant approach, but I think I'll just walk through our logic of looking at these types of trust calibration methods, because then they make themselves their way into the various kind of factors that we have in building a reward criteria. So the first one is kind of establishing some baseline. So what are the traditional metrics? This I'm sort of looking at like these crowd wisdom models. What are the traditional metrics used by 3D AI researchers? Things like cosine similarity or structural similarity for looking for artifact detection in the structure of an object, or like an LPIPS for detecting artifacts within the texture space of an object. Then, baseline is good, but can we make this more exploit proof by thinking about consistency in the quality scores between models, using things like visual language models to curate additional quality metrics and classifiers, and then finally looking at kind of dynamic ranking. So in our case, and I'll spend a bit more time on this one because I probably one of the most interesting aspects of what we're building would be like an ELO ranking system that rewards and punishes based on visual language models. And then throughout, we are also fortunate or unfortunate in the subnet that because it's such a visual subnet, you can have human in the loop come in multiple stages. Looking at checking the outputs of duels, looking at generated models, and understanding all of that. So yeah, so this is when we started. This is what we looked at as a year ago or so. This was the result of a colorful fish, and it's cool and it's very fun. It's probably not game ready in many respects. And now we've seen that the subnet has just really made a tremendous amount of progress in the realism and quality of the models that they're generating. And this is kind of how our validation mechanism has evolved. A bit overly simplified here, but like first looking at just prompt adherence. So are the generated models a reflection of what the user was asking for? And that's good, but that then opens you up to problems of, well, maybe this is the requested model of the user, but it's not very high quality, even in whether it's a subjective or objectively high quality. And so that's where you start to put in some of these additional metrics coming from, agreement and consistency, as well as some of the artifact detection methods in structure and in texture space. And so now all of a sudden, can you balance if something is both a high quality model and does it match the prompt? And there's always trade-offs here. There's always a little bit of a balance between the two that we as sort of subnet owners are adjusting as we sort of are seeing how the subnet is trending, as we see where miners are innovating and pushing. And then the third constraint in our case, but I suppose in many subnets as well, is what are the user-based constraints that we're going to put in here? So if you're generating models in the gaming industry, especially for something called user-generated content or UGC, you want to have those models quite quickly. So there's a time budget allowance for the generations. And then we've heard recently from users that they want to input 2D images to generate the 3D model. So that's what's on testnet next week. And then do we want to start to include mesh and other formats here, or do we want to do this through like open source post-processing tools? And then finally, what I'm going to talk about, because I think this is kind of interesting, is the dynamic evaluation with an ELO-based system. So this is an example, a real example of two models being evaluated by a VLM for an ELO battle that they have. So in our subnet, the next iteration of the validation mechanism is actually going to have a balance between fast validation and slow validation. So slow validation will be a little bit more computationally intensive and will head-to-head battle with an ELO ranking system, whereas fast validation will basically be used to keep all the miners on their toes and rewarding users with models very quickly, which aligns with what the industry expectations are. But if we look at this ELO ranking system, in this case, this one's pretty easy. You don't really need a battle to tell you that the model on the left is lower quality than the model on the right. It flags things like blurry, abstract shapes, poor image quality, lack of focus, doesn't therefore really represent the prompt. There's no visual artifacts versus the right one. When we look at these two, which is kind of the original one that prompted this, is here, what the model looks at, it says, okay, they don't find visual artifacts or structural artifacts in either generation. So that's very positive. But at the same time, you've asked for a sturdy yellow drill cordless, and the model on the right has a large amount of teal in it. So that's not particularly well aligned to the prompt. And then the second thing, and this I thought was quite interesting because I actually didn't catch this when I was looking at the results, is the model on the right has this base on it, which isn't bad, but that's not asked for at all by the user. So one can assume then that the user probably didn't want this to be included. And so based on that criteria and with that rationale, which we will apply to the miners so that they can also sort of understand why they lost some of their battles, the model on the left wins. And what we found in our internal testing is that these VLMs are not particularly good at an absolute ranking. So it doesn't make much sense to compare the 8 that this model received against the 9 that this model received. But they are very good at a relative ranking for two models head-to-head in the same competition. And so the relative winning of 8 versus 7 tends to be reliably good. And then we've used that across kind of different, we've tested across different VLMs, and in the end, yeah, we're pretty happy with where that's at. So that's kind of how we're dealing with this. And then, where does this go? So this is probably some of the more fun part of the presentation. What are people using this for at the moment? The first thing I would just flag is that, there's value in the results here that don't win. So like in this particular example, it would be a shame, or it is a shame, that although this model didn't win, it didn't go back to the user, it's not lost. So what we do is we add that to a data set for an open source data set for AI research. We've built the world's largest data set. We announced this a little while ago. And we're actually larger than all of the other data sets combined, which is amazing. We've had outreach from academic institutions and researchers to have access to it, to build on it. It gives us a lot of interesting potential to do asset store iterations off of this, and of other kind of pretty interesting effects there. With the models that win, there's use cases within games. So here, for example, is a gameplay trailer that somebody made that I quite like. So in all of this, the VFX are not generated by us, but everything else that you see here is. So all of these cars are, the rocket here is, the models in the background, the models in the foreground. You can see that they have physics applied to them. They work very well in existing systems. This is in Unreal Engine. Yeah, they turn over, and they're weird as well. I mean, that's also one of the things of generative AI. You're not limited to the world around you. I think all the cars are kind of dogs a little bit. Yeah. This was an in-house project that we did, which is interesting. So this was one of the first times that we wanted to showcase what the technology could do. So these are all splats. You see outlines of some of them, not even all of them here. I think this particular world had about 20,000, no, maybe more, about 30,000 splats in it, which was a little bit of a testament to show that you can have a huge diversity of models to create realism. And then it's not just some abstract concept. It's not just make this world in Unreal Engine. We'll actually go ahead and publish this game so that people can play it. People can see the quality of the models up close. We'll probably put in some basic gameplay mechanics, like finding different splats that are hidden throughout the world. Maybe we'll even do some rewards with some cool merch and physicals that we'll print off and send out to people. So I think stuff like this. One of the nice things about the outputs of our subnet is it's very understandable, not only by a Web3 audience. So I think things like this have the ability, hopefully, to go beyond just Bittensor's community, even to some extent beyond Web3 communities, and engage people in ways that maybe they didn't realize that this type of worlds and scenes were capable of being generated today, with models that are basically beyond state of the art for what they know about, because they're being run on Bittensor. This is a very interesting project as well. So this is currently on display in Venice at the Architecture Biennale. I don't expect that there are too many architects in the audience. I'm actually trained as an architect, not just a software architect, but a built environment architect. And for me, the interesting thing is that the Venice Architecture Biennale is really like the absolute pinnacle or apex of the most prestigious architecture and art festivals that you can exhibit at. So when I was in architecture school, it was always like a dream to be exhibited at the Architecture Biennale. And then I never really pursued a significant career in architecture. And then somehow through 404, we ended up having a slot there. We were asked by the curator of the Biennale to exhibit an AI generated piece. And these are 11 different AI generated in Unreal Engine. They tell a little bit of a story because there are certain characters that follow them through, but that's not really super relevant here. I think to me, what's really impressive is just the quality that one can achieve. And this is an Unreal Engine, which for those unfamiliar, engine, so this is not a professional production by any means. I think to achieve this level of quality, one might think that you're working in a huge studio with a huge budget, but actually this was done by 2 people over a couple of weeks. And the really remarkable thing is that these 2 people are not 3D artists. They're not trained to model and texture. They are just highly creative. They're good at composition. They're good at lighting. One is the other is a creative director. And this is exactly where I think this tech should be deployed. I think this tech is really about, there are people who are not trained in this industry, and that's the bottleneck of 3D content creation. That's the bottleneck for gaming. That's the bottleneck for film. That's the bottleneck for immersive worlds. But they're able to participate in this ecosystem, and they're able to manifest kind of their crazy visions, which is really nice. We're also I just came back yesterday from Japan, because we also have a piece in the World Expo in Osaka, similar idea. And again, it's I think Osaka's going to have like 28 million visitors that have no idea about crypto or Bittensor. And for us, it's really great to be there with information about Bittensor, about Tau, about the subnet, about all of the stuff that's being built there, because I think that's exposure to a bit of a new audience, which is cool. This is another game. This game is really interesting to me for 2 reasons. One is it was essentially done by somebody, it was done in Unity. So it was done by somebody who's never used Unity before. The gaming industry landscape is split. There are 2 major game engine companies. One is Unreal Engine, which is the other worlds that we've shown so far. And one is Unity. And arguably Unity is the better fit for us, because Unity is targeted more towards like indie game developers and things like this. And the guy who created this had never built anything in Unity before. So he generated all of the assets on 404. And for all of the game mechanics, like the movement of the car and like the boost you get going through the hoops, he just used Claude to vibe code this basically. And to me, that's like kind of insane that somebody can open up a software they've never used before and then make something like this. And then the other reason that this is really interesting for us is we announced it a couple of weeks ago, but we are a verified solution. That may not sound like a big deal, because we don't need to be a verified solution in order to put 3D models on Unity, but it's actually a very big deal for us, because it means that Unity went through an extensive amount of tech due diligence to look at our tech stack, understand our tech stack. We were just saying, you were just saying before the call started, Const, that like you were talking to this researcher, and part of it was explaining to him or helping him understand that it's not that when you look at something like Bittensor, when you look at a subnet on Bittensor, you can write about it, or you can understand it, or you can test it in the case of Unity, because you believe in its incentive design, you believe in the way it's validated, you see that, for example, the code that we put forward is all of the correct licenses, and we're doing everything that we can ensure like stable quality, if not like continuously improving quality, comes out of it. And so that's a really big Web 2 testament that then is now generating direct off mainnet. So for us, that was a really big win, to be honest. Then we see a lot. Oh, sorry.
And you mind if I just jump in here and ask some questions, because I'm really curious. So we're looking at assets generated with 404. In this video right now, which assets, like the buildings to the right and left of the track, like the fire,
everything that's not VFX. So like the fire The moving fire, for example, that will be like a visual effect. So it's a dynamic asset, the fire coming out of the back of the car, but everything else.
So when you say everything else, you mean that somebody prompted, skyscraper,
Yeah,
futuristic, and put it there on the right.
lamp, sign, tunnel, panel. Yeah.
And how many assets are we talking about in this video? Because it looks like thousands.
I mean, some of the other worlds include thousands. I don't know. In this one, to me, it looks like they use a bit of repetition here, so maybe hundreds. But yeah,
But let's take me through how this works. So as I'm trying to generate this game. I've never made a game before, but it sounds like I should probably start. I need one of these arrows for the side of the road. Do you think that they generated that particular arrow, or was this just like general a track piece? How did they get it to match with the previous track piece? How do they get the angle to be the correct angle for the side of the road?
so they'll manually like compose them together. So you'll start generating. So I think the process here is you'll start generating like track piece components. So you'll start prompting, you know, racetrack, floor, or maybe like sci-fi panel, something like this, and start just kind of basically resubmitting that prompt and developing yourself this little like library of these kind of flat surfaces that you want to be the track. And then you'll just align these together. So you'll just go in Unity, you'll just use like a gimbal to move and scale them into sort of the order that you want. Then you'll do the same for things along the side of the track. So especially like these tunnels, and then you'll do all of the stuff in the background. So the skyscrapers and the antennas, the light posts, things like this. Yeah.
And so how do you generate like consistent look and feel? So I mean, like, okay, I've got one arrow over here and it's this size and it's pointing this direction, but now I need one for the ground. How am I going to ensure that there's that style transfer that is required to make a cohesive game?
Yeah, so when you're text prompting only, it is a bit of a challenge. So I think it's a lot of just trial and error there, and you can be a bit descriptive with your text prompts by using like cyberpunk style or something kind of relatively descriptive. But one of the feedbacks that we've had from people who have been using it is, hey, we would to use images as inputs rather than text prompts because we can get a more consistent style, especially when we're generating kind of this massive amount of assets in it. And so, that's what's going on to testnet next week. But
Okay,
yeah,
so cool.
that would be another way that you can do it.
I can take a picture of a building and put it into a VLM and get it to output a prompt, and then take that prompt and put it into 404, and it would generate something more or less like that building because it's outputted a pretty detailed description.
Exactly. But from next week, you'd also just put that image directly into 404 and then just skip the VLM part of it.
That's so cool. So just to put this in like context, let's say that I'm an indie game developer, but the year is 2021. Bittensor is still trying to do information validation. It's not working very well.
Yeah.
How long and how many people would it take to make this, and how expensive would it be to make what we're looking at right now, which looks like a really fun game? I kind of want to play it.
So the information that we have is basically, in general, when you make a game, the 3D content creation is about 30 to 60% of the game budget. And then you're gonna have now probably a team of 3D artists that are gonna have to first make the model. So without textures, that's the first step. And some models will take longer than others. And the second step will be texturing the model. So painting, for example, or like using Substance Painter, for example, to paint, or using images sort of stretched across different things to do that. And so a game like this, I'm guessing, if you're an indie studio, so you're not a huge team, maybe you're a team of 10 or 15 or something like that. Yeah, it's going to take you at least a few months, maybe 6 months or something to create something like this. And that's been quite that's being quite advantageous though, because that's assuming that you know exactly what you want before you start doing it. I think what we realize is that in the gaming industry, a lot of the difficulty comes in that you want to iterate. You want to just be, especially in what's like called the pre-production phase, you just want to explore different ideas and concepts. But without AI or in traditional systems, the iteration is about as fast as the individual as the sort of from scratch asset creation. Not 100%, but it's not very easy. Manual modeling is not a non-destructive workflow. It's a destructive workflow. So if you want to go back to an earlier point in time, you're going to lose that progress and you're going to start again in your content creation. And so I think a lot of times, actually, I'm speaking at like creative conferences or gaming conferences, things like this, and the creative industries is inherently a little bit skeptical or cautious about AI solutions, right? I mean, I think that's one of the industries that has been one of the more outspoken ones against AI. But I think for us, it's always about flagging for people. Look, this is just a way to be more efficient in your creative process, to do more with what you have. If you're a team, you can make a because you can be that much faster. If you are a single person, you can explore more ideas and then gravitate on one and develop it. I mean, this comes even a little bit from my own personal work as an architect. I used to do architecture competitions. So when you get a competition, you'll have something like a 2-month deadline to submit your design proposal. And that means you might have 100 really cool creative ideas for what you want, but you don't have time. You have time to mock up maybe 2 of them. And so you're going to just make a guess or go with something and try it out. And as a result, you're not able to fully embrace the creative process. And I think that's like that's a big selling point for people in this industry is not necessarily that like it's going to do everything for you, but it allows you to focus on being creative a little bit more. It allows you far more faster, so you can either do something that was previously not possible with your team size, or you're just able to do it a lot more creatively.
And so I might be kind of getting ahead of myself and ahead of you in this presentation, um, but this is just for video games. But the space of problems that you could be solving with 3D models is not just video games, right? It's CAD, it's architecture. No?
Yeah, that's that's what I was trying to say in that sort of slide where like 300 billion is the gaming industry, and so that's why sometimes people focus on gaming. Gaming is a huge market, but digital twins, we've seen people trying to use this for digital twins, for film and VFX, for things like metaverses, things like XR is another just incentives and